we're going to look at solutions. So we looked at things like, are they linear dependent, linear independent? We looked at boundary conditions, but now what we're going to do is we're going to look at how we can kind of analyze the solutions. And there's some backgrounds. There are quite a few slides here, but I'm going to just hit the high points. The first thing is if you take a peek at this is just our regular old linear differential equations. Something y double prime, something y prime, something y, something without y's. And so if you look at this, they don't have the something without y's because it's equal to 0. That's homogeneous. So homogeneous means equal to 0. For if it's not homogeneous, okay, we say it's not homogeneous as if this is equal to something other than 0. So we would say everything's the same, something times y double prime, something times y prime, sometimes y equal, instead of 0, it's equal to g of x. So what does that have to do with anything? Well, you know, with the examples you can see this one is, which of those two? Not hard. Homogeneous. And what's this one? Non-homogeneous. Okay. So a lot of times they're going to give you some solutions, and when they give you solutions, we're going to assume these three things. Coefficients are continuous, like the x's or the 3's and 5's. If it is not continuous, or if it's non-homogeneous, that right-hand member g of x is continuous. That is going to be a big deal that we won't even talk about, we just kind of assume. And then the first term is not 0 because then it wouldn't be the differential equation we're looking at, first, second, or third order. So if we're looking at third order, that means we have y triple prime, and what's in front of it isn't 0 because then it wouldn't be a third order, it would be a second order. All right, so superposition, all you're doing is when they give you solutions, okay, you can put them together into one big answer. In other words, if this was a solution, this was a solution, and so on, you can add those up and it will make one grand solution. Superposition. Look at this proof real quick. I think it's kind of neat. So let's say we have y1x and y2x as solutions. Okay? So y1x is here, y2x is here, and we're going to multiply it by a constant, c1 and c2. So these two are given as solutions, and then we're going to put that into one big solution, superimpose them together. Then what you'll do is take the derivatives of each of these, and I'm going to do that right now. So y prime is c1 y1 prime of x plus c2 y2 prime of x. And then the second derivative is going to be c1 y double prime of x plus c2 y double prime 2 of x. There's a 1 here. All right, when you put them together into this, you can see you have your a2, and you'll just get the 2 that we had here, c1 y double prime plus c2 y double prime. Then we have the next part, a1 of x again. That's a different coefficient. And then that's going to be c1 y prime plus c2 y2 prime. And then the last one is going to be a0 of x, just another coefficient. And then these, that's the original solution, y1 times c1 plus y2 c2. But look what happens when we multiply these through and then break them up. Because of the c1s that appear in each one, we can put those together, pull out the c1. We can put the c2s together and pull out c2. And then this part here, this whole thing, is equal to what? Yeah, because that's what's given right here. That's given to be 0. And this whole thing here, also 0, because that's what was given. And since there's 0, C1 times 0 plus C2 times 0 equals 0, that means that we've verified that that works. And all it is because when you take the derivatives of these, they don't change. Only the function changes. Corollary, you can multiply your answer by C1 and it won't affect whether it's homogeneous. And I think I like this example 18. So would you go with me, would you write on a blank spot? We're going to do number 18 here together. I don't like them having done it, so we're going to do it. Y1 equal x squared, y2 equal x squared with ln of x. And we're looking at the equation y triple prime, right, times x cubed minus 2x y prime plus 4y is equal to 0. So here's what I'm going to do. I'm going to break this into two parts, here and here, and I'm going to have you take y1. Let's have this side of the room. You're going to do y1 equal x squared. Take the derivatives. And then put it into this equation and see if it works. Same thing. Do the same thing here for y2, this half of the room. So y2 is equal to x squared ln x. Oh, congratulations, you get the product rule. Y2 prime, y2 double prime, y2 triple prime. Go ahead and do that. And as we're working through these, we'll find that this is just 2x, this is 2, and then this will be 0. This is going to be x squared times 1 over x plus 2x times ln of x, or just x plus 2x ln x. And this derivative will be 1 plus 2x times 1 over x plus 2 ln of x, which is 1 plus 2 ln of x plus 2, right? X's cancel. So the third derivative is just going to be 2 over x. Does that look about right? Is that what you guys got? All right, so now for this one, we're going to use this equation and verify each one. So this one, we're going to take x cubed, the third derivative is 0, 2x times the first derivative, which is 2x, plus 4 times y, which is x squared, and we want it to be 0. Here, this is 0, so you get negative 4x squared plus 4x squared. It works. So that one's verified. How about this one? X cubed times y triple prime, which is 2 over x, minus 2x times y prime, which was x plus 2x ln x. And then the last one is plus 4x squared ln x. And that hopefully is going to be equal to 0. So we get 2x squared minus 2x squared minus 4x squared ln x plus, how are we looking? Is it going to be equal to 0? Oh yeah. So those are verified. So what? Who cares? Well, what they're trying to show is that what if my solution was a combination of these two? So we verified those. But what if we said, all right, these I showed our solutions. Now I'm going to come up with another solution. It's C1 x squared plus C2 x squared ln x. and that's going to be equal to y. This is my general solution. Is that going to work? Well, if you can show that the individuals both work, then you can show that this works. Let's do it. So we're going to have to take the three derivatives, which won't be hard, because we've kind of done it already. 2c1x plus, oh boy, help me out here. This was c2x squared times 1 over x plus 2x c2 times ln x. The second derivative is going to be just 2c1, and then this is just going to be x, so it's just going to be c2x. This will just be c2, am I right? And then this one's going to be plus 2xc2 times 1 over x plus 2c2 times ln of x. So now when we do the third derivative, these will be 0. This will just be 2c2, right? Because the x over x. Oh, no. This will be 0, won't it? And then this is just going to be 2c2 over x. Does that sound right? All right. So then when we put this back into the original, we're going to get x cubed, third derivative, 2c2 over x, and then we're going to minus 2x times y1, 2c1x plus c2x plus 2xc2 ln x, and then it's going to be plus 4 times c1 x squared plus c2x squared ln x. Hopefully it's going to be equal to 0. And I kind of made it so it was hard for me to have room here, so I'm going to fix that. And that's fine. Group. And hello. Good. And then let's just move this up here somewhat. All right, so then I'm going to rearrange this, and I'm going to get x cubed over x is 2c2x squared minus 2x times 2 is minus 4. Help me out if I'm making a mistake. c1 minus 2x squared c2 minus 4, right? 4 c2 x squared ln x plus 4c1 x squared plus 4c2 x squared ln x. Is that equal to 0? Do we see things cancel out? These will, right? These will, and these do. So what we showed is that if these are solutions, then you can generate a grand solution by just saying that y is equal to some constant times the first plus some constant times the second. That's going to be a solution for you, for a homogeneous solution. This is pretty much the pivotal part of this whole lesson. Then all that you're going to do with the rest of this, you can verify these. Do we need to go over this one? You've got either the x, either the 2x, either the 3x, and they just said that the solution would be c1, either the x, c2, either the 2x, so on. That makes sense, doesn't it? We don't have to do anything more with that. All right, constant multiples. So that's where the c1 comes in. So you can, when you say y is equal to x squared, you can also say y is equal to cx squared. And so that you can prove with all those examples, but it's just the same thing. We want to show that they're independent, and then we do that Wronskian that we did before. There's a proof here for that. I'm not going to go through it. You can read it if you'd like. Dealing with those constants, those C1s, C2s, this works as long as it's linear independent. So doing the C1 solution, f of x1 plus C2 f of x2, that only works if, actually we'd set this equal to y. This only works if these two are independent. That makes sense, doesn't it? Why does that make sense? If they weren't independent, they were dependent of each other, they would just form one with one constant. So that's why we have to look at that independence. And they had a proof, nice proof with that. Existence of the fundamental set. We talked about homogeneous linear. That's what we were looking at. And we looked at finding the general solution. So that's what we just did. We just handled that nicely. They're proving that these are independent of each other. They proved that first, and then they made the general solution for that. So I don't think we need to go any in more depth than that. And then sometimes they're not homogeneous. So sometimes you're going to get non-homogeneous, and all that happens is there's something, it's equal to something other than 0. But something other than 0, all you have to do, and look up here for a second, all you have to do is solve it like we just did, get that solution, general solution, and then we'll add what at the end? You just solve this for your general solution, and then just add this at the end. That's all you have to do. So one more time, the whole point of this is that I'll give you a couple of solutions. You need to know that they're homogeneous, or they're independent, and then you can just put the C1, C2s, and so on. If it's not homogeneous, you just tack this on at the end. And this doesn't have to be one term, it could be a whole bunch of terms. That's what they're showing here. Here's just a one term, but then you can have a whole bunch, a host of terms to deal with, like this one has 2. All right, so I think that's a good overview of it. Take the solutions, put C1, C2, C3 if there is, and then if you have this equal to something other than 0, like this one's 3x, then that's going to be tacked on. I think, like that. I think that would be good. So let's go to some problems here. You have to exit out of this last sentence. So we're going to start with just doing number 31. It says, verify this solution is of the nonlinear equation y double prime equals 2y cubed. Is this homogeneous? Would you call this homogeneous or non-homogeneous? Well, you might think since there's something over here, it's non-homogeneous, but because it's y, it's related to y double prime, we would call this definitely homogeneous. And then verify that 1 over x is a solution. So all you have to do is, this is old news, x to the negative 1, y prime is negative x to the negative 2, y double prime is 2, x to the negative 3. So you put those in. 2 over x cubed minus 2 times 1 over x cubed. Is that going to work? Does that work? Oh yeah. Perfect. Okay. And then 0 to infinity, that's just the interval because of the 1 over 0. I don't know why the negatives wouldn't work, why they can't, but they don't include 0. Show that the constant multiple is not a solution for this. So if we go y equal to cx to the negative 1 and y equal to cx to the negative 2, y prime, negative c, y double prime will be 2cx to the negative 3. And when we put these in, the second derivative, 2c over x cubed minus 2 times c over x quantity cubed. Well, this looks fine to me. Is it right though? Does it work? Why not? The c gets cubed, so you're going to get 2c over x cubed minus 2c cubed over x cubed. That will not be equal to 0. What if c were 0? Yeah. So there's a couple things we're going to leave out here. C is not equal to 0 because you're right, 0 would make it true. And then if you put a 1 in, c is not equal to 1 or negative 1. Either one of those. Negative 1, this is negative 1 cubed. This would be positive, this would be negative, it would work. So we would say that it's not a solution unless c equals negative 1, 0, or 1. Kind of confusing writing on there, those. There you go. So that's a start. So what you're going to do with 33 and beyond is you're going to show that these two are linearly independent. Make sure you check that. And then do your general solution and prove those. I would get the general fundamental set, they call it. Get that general solution and just do that. Don't do the individuals like we did. That was just for an illustration. And you'll do that for each of these. These will be challenging. Some of them will get a little long, but just go through those, and I think 43 is the last one. And if you want to try 48, you've got it. And all the answers should be in the back.